Welcome to Uncle. Good evening to all. Good evening, everyone. Good evening.
Good evening, sir.
Good evening.
Happy Teachers Day, sir.
Thank you.
Happy Teachers Day, sir.
Thank you, Rita. Thank you, Abe. Thank you, everyone.
Okay, take my bow.
Thank you, everyone.
Good evening, sir.
Good evening. So let us start. We just started with the problems based on Carnot engine. I think we discussed only one or two problems based on that. Now, next one, a reversible heat engine. It converts one-sixth of the heat input into work. So it clearly means that the efficiency of this particular heat engine, it is 1/6. When the temperature of the sink, good evening, Uzma, thank you, is reduced by 62 degrees centigrade, then its efficiency it gets doubled. You have to calculate the temperatures of the source Thank you, Mamta. So this is the question. First of all, calculate the efficiency. Okay, and obviously efficiency is related to temperature of sink and the source. So we will get two relations. Okay, with the help of old efficiency and doubled efficiency. So two relations, two unknowns, and we can solve that. Okay, efficiency is W by Q, and it is given that this is 1/6 of Q. So efficiency is 1/6, and it is nothing but 1 minus T2 by T1. Okay, so it means T2 by T1, it is 5/6. Why I am converting T1 in the form of T2? Because we require T2 only. No, we require T1, T2 both. So let us convert it in one variable only. If I'm able to get T2, obviously I will be able to get T1 also. Now new efficiency, it is doubled. Doubled means it becomes 2/6. And when the temperature it is reduced by 62. Okay, the difference is always same. Whether you call it 62 degrees centigrade or 62 Kelvin, it doesn't matter because this is the reduction in temperature. Okay, clear? Two by 3. So T3 T2 minus 62, 2 T1. So it will be 2 into 6 by 5 T2. Now please solve it and get me the values. No, Rita, it's not the correct answer. 93 is is the value of T1 or T2? Is it the value of T1 or T2?
T1, sir.
No, it cannot. Let us check what we are getting. I have solved it almost. Now you have to just do 2-3 steps only. Everyone noted from this slide? Have you noted?
Yes, sir.
So 3T2 minus 186, it is equal to 12 by 5 T2.
$372 आ रहा है सर.
T2 is this one.
310. 310.
Correct. And then T1 was 6 by 5 T2. No?
Yes, sir.
372. 372.
372 आ रहा है.
Okay, now it's correct. So this step is tricky actually. What some of the students they will do, they will start adding 273 to this value and then they get it wrong. Because it is the reduction in temperature. This is not the absolute temperature. Okay, reduction is same whether it is in degree centigrade or Kelvin. So it has to be retained as such. Okay.
Yes, sir.
A heat pump it is actually a refrigerator. According to the question, it is working like the refrigerator. It is taking heat from the cold source and giving the heat to the hot source. So we need to calculate Q1. So T1 is 0, that is 273 Kelvin. T2 is 22, that is 295 Kelvin. And Q2, 450. Actually, the diagram is like this. Room is at temperature T2. Outside air is at temperature T1. It is taking heat Q1 from the outside air and doing some work, and sum total of them, Q2, it is given to inside of the house. But we know that Q1 by T1 is Q2 by T2. No?
Yes, sir.
So Q1 will be Q2 by T2 into T1. That's it. So now substitute the values. 450 kilojoule per second. T2 is 295. It is 273. So obviously Q1 has to be less than Q2. So how much are you getting? 417. Is it? Please check.
Yes, sir. Yes, sir.
Yes, sir.
Four one nine आ रहा था.
Really? Are you getting 419 students or 417?
417.
Then please check your calculation. We are getting 417 only. Let me check also. It's 416.44. No? Not even 417.
Yes, sir.
A reversible Carnot engine. This one. Very good, Siddesh, Abhay, Rita, Arun, very good, Mamta, very good, Nisha. Yes, Ritika, Kapil, good. Gautam, it's wrong. On what factors the efficiency of the engine depends?
Temperature.
Only on the temperature. The efficiency of Carnot engine is independent of the nature of working substance. So it doesn't matter whether we are using the photon gas. It only depends on the temperatures of source and sink. Depends. Therefore, in this case, it will be T1 by T2 because T1 is less than T2. So T1 is the temperature of sink, T2 is the temperature of source. Clear?
Yes, sir.
Yes, sir.
Work done per unit time. Air conditioner. Again, it is like a heat pump or refrigerator. Takes heat from the cold reservoir and give it to the hot reservoir. 27 plus 2, 73, 300 Kelvin. Heat taken out. Work done. And then heat given to the surroundings. Temperature is 47 plus 2, 73. That is 323 Kelvin. Not 323, 320. 320, na?
Yes, sir.
So now we have to calculate the minimum work done. Okay. Now, what is coefficient of performance of the refrigerator?
Theta equal to 1 upon eta minus 1.
That is AC in this case. It is beta equal to Q2 by W. Can I write it as Q2 by Q1 minus Q2 or T2 by T1 minus T2 like this? Okay. So Q2 is known to us. This is per unit time na? Already. Watt na? W we have to calculate. T2 and T1 they are known to us. So you can calculate W na? By substituting the values now. Okay. Please do it. Very good, Siddesh. Divya, it's wrong. It's wrong, Rita. Yes, Arun, very good. If you want to take the difference, you can take it in centigrade only. Okay. But because now we have converted them, let's write it in Kelvin only. 7,000 into 20 by 300. 466.67. This much?
Yes, sir.
Please check everyone. Please solve it. Very good, Arun. Very good, Kapil, Rita. Just now we did it. Everyone should know. Try to get Q2 from here. You will get your answer. means you will be able to eliminate two options at least. In fact, you are getting the answer now. Yes.
Yes, sir.
So it is very clear that it is D option. But let me tell you about Q1 also. How to get it? Eta is W by Q1. Q1 minus Q2 by Q1. This is the first relation. Okay. So this gives clear. And Q2 we have already done that. Or if you want to solve for Q2 from here, because that was the refrigerator case, you will say. But if you want to do it for this one particular, then what you can do is you can substitute for W. W is Q1 minus Q2. So if I substitute for Q1 over here, then I will be able to get Q2. W is Q1 minus Q2. This gives me Q2 equal to Q1 minus W. So Q1 is W common. Clear? Is it clear to all?
Yes, sir.
Yes, sir.
Now this is important type. Two engines in succession. Very good, Arun. It's wrong, Sunita, Rita. Very good, Abe. Very good, Kanaya. Very good, Kapil. Is this diagram clear or should I make it on the next slide? Let me make it on the next slide. It is very crowded. Okay, first of all, try to understand what is happening. See, first engine, it works between these two temperatures. It is extracting heat Q1 and giving out heat Q2. And this whole heat, it is taken by this one. And it does some work and obviously it leaves heat Q3 now. Obviously, let it be W dash. Clear? Now, if I try to obviously let it be W dash. Clear? Now, if I try to calculate the efficiency, what will be the efficiency? Total work done is W plus W dash, and the heat taken is Q1. Na? If I see this portion and this portion, okay, this is the heat taken. Clear? And the total work done is W plus W dash, and W is Q1 minus Q2, W dash is Q2 minus Q3 by Q1. Q2 will get cancelled. So I'm left with Q1 minus Q3 by Q1, and it is nothing but 1 minus Q3 by Q1. And we know that Q3 by Q1 will be equal to T3 by T1. So here is the answer. Clear?
Yes, sir.
Yes, sir.
So always remember, it only depends upon the initial and final temperature, not on the in-between temperatures. Okay, so mark this important. This is a good question. Now, two Carnot engines, A and B, are operated in series. Engine A absorbs calculate T. Okay, so please solve this. I'm coming. Take your time. So remember, work done is same. Okay, work done in both the cases, it is given to be equal. So this is very important. So you can remember the result of this question as a generalized formula. Let us make the diagram. What the first engine is doing. Temperature T. We can say T2 is equal to T. Na? Let's call it WA because this is substance A. Na? And then let us write the equation for this one. Efficiency of this one will be 1 minus T by T1 or 1 minus Q2 by Q1. Let it be number 1. This one is okay. Now, because the two engines, they are operated in series, second engine, it is absorbing half of the heat rejected by engine A. Now, please keep this thing in mind. Half of the heat. T. And heat absorbed is half of this by B. Okay, and work done is same. Work done is same. It is equal to WA. And let us suppose it gives out heat Q3. And is this given? This temperature, something?
200.
Okay, very good. So let it be T3 equal to 200. Now, what will be the efficiency of the second one? Eta B. 1 minus T3 by T, na? Or 1 minus Q3 by Q2 dash. Or we can write it as 1 minus Q3 by Q2 by 2. Is it? Number 2. Now, because WA is equal to WB, so WA is Q1 minus Q2, and WB will be Q2 by 2 minus Q3. Na? So Q1 minus 3 by 2 Q2 plus Q3 equal to 0. So dividing throughout by Q1, because we are having, yeah, so we will be able to get Q2 by Q1 that way. And from there we can get Q3 by Q2. Na? Okay, so divide by Q1. Or you can do it for divide by Q2 also. Because if you divide by Q2, this will become Q3 by Q2, this will become Q1 by Q2. Isn't it? So either way you can do it, whatever way you like. So you just have to get the value of Q3 by Q2. Let me do it. if we divide by Q2, so what is this Q3 by Q2? Multiply and divide it by 2, because it is 2 Q3 by Q2 now, over here. So now, see here, I know the relation between this 2 Q3 by Q2 and T3 by T, isn't it? From 2, I can say that 2 Q3 by Q2 is T3 by T. And this Q1 by Q2 from here, Q2 by Q1 is T by T1. Let me write it here. So T1 by T is Q1 by Q2. Okay, so T1 by T. So now I think we can solve it for T, isn't it? So 2T is the LCM. 2T. First of all, let us write it in this manner. So of course, 1 by T can be taken as common. So it will be 2T1 plus T3 by 2. So this 2 and 2 can be cancelled. So T will be is it? What is T1? 500, T3 is 200. This is the answer that we were looking for. Please check. This is how such question should be solved when the work done they are given to be equal. Okay, let us do one more. Here, of course, half of the heat was being absorbed. So that's why we are unable to get some convincing type of general formula. This formula is not so simple actually. So now we will generalize it actually in this particular question. So again, the work outputs. So now you have to solve it yourself. So two cases when the work outputs are equal and when the efficiencies are equal. So now you can remember this result, because in this case, the heat rejected by the first, it is being used by the second. For A, no Saket, this is wrong. This I'm doing for the first part. Okay, let me write their efficiencies also. Now first part. Mamta, what do you mean when engines are equal? It is either work or efficiency.
Sir, work.
Yes, it's correct. No, Ritika, it's wrong. It's wrong for A part. Sanket, it's correct for B part. But for A, you are saying same for A and B. Na? Yes, Abhay, it's correct. Now for A part, WA is equal to WB. That is Q1 minus Q2 equal to Q2 minus Q3. So Q1 plus Q3 equal to 2Q2. So Q1 plus Q3 by Q2, it is equal to 2. Okay. So can I write T1 plus T3 by T2 equal to 2 from here? We need to get T2 now. Okay, it was at temperature T. So T2 is equal to T in our case. Okay. So you can replace T2 by T actually. Okay. So it means the general formula is when the work outputs are equal, that the temperature is the mean of the temperature of source and the final sink. This formula you can remember. Okay. 650. Na?
Yes, sir.
So now in the second case, efficiencies are given to be equal. Efficiencies are given to be equal. So 1 minus T by T1. So now the temperature will be the square root of the product of the temperature of source and sink. Clearly 600 Kelvin. Na? Mamta, it's 600. Please check. I have solved it, and you can remember these generalized formulas also. Clear? This
Yes.
is important one. Mark this important. You are getting two generalized formulae. Okay. Yes, Sanket, we will be doing that. I said it earlier also. We will be doing that. I will discuss that with you when we discuss about phase transition and critical temperature, pressure, those quantities. Right now, for you, it will be just an equation, but the real application, it comes over there. So that's why I have not discussed that. Now, this is the case which I was talking about yesterday. Because heat is being transferred from one object to another. So it is not having an infinite thermal capacity now. It is having some finite heat capacity. So heat capacity, it means its temperature will change when we go on extracting heat from the object. So when the temperature will change, then it is a efficiency is a variable quantity. So we need to integrate it to get the total work done. Okay, so dW, first of all, dW is eta dq. And eta is 1 minus T1 by T2. Na? Because heat is taken from an object at temperature T2 and is given to a reservoir at temperature T1. Okay.
Yes, sir.
Eta is variable. Okay, and eta equal to this value is variable. So W will be, can I write this dq as CP dt? And it will be dt2, na? log T2. This option B, na?
So can you please the previous slide just for once? So theta is d2 by d1
Guys,
d1 by d2 or d2 by d1? Theta.
read the question. What is the temperature of source and sink?
Okay. Okay.
Temperature of source is T2 over here, na? And the sink is T1. So accordingly, we have to modify the formula. Na? Clear?
Yes, sir.
Yes.
And one more thing, I have taken it T2 here, so it is already maximum that we can get. Okay, because T2 is greater than T1. Na? So this is again important type. Now, this one. The heat capacity of the interior of a refrigerator heat capacity is given and the change in temperature is also given. So you can calculate Q2. In refrigerator, heat taken from the cold substance, it is denoted by Q2. Na? And W is Q1 minus Q2 na, in this case. Again, because Q2 plus W is Q1. So what is the heat removed from the refrigerator? It is given to be kilojoule per Kelvin. So 4.2 into difference of temperature. 4.2 kilojoule. Please check. This difference will be same now whether you take it in degree centigrade or Kelvin. Okay. Now heat given to the outside, heat given to outside, to the outside atmosphere. This will be fine. Q1, Q2. Now we are taking the outside temperature to be T2 now. If we are taking the outside temperature as T2, let me write T out by T in so that there is no confusion regarding T2, T1. This will be fine. So Q2 is 4.2 kilojoule. T out is 27. Now it should be in Kelvin. It was 18. So 4.2 kilojoule, 300 by 291. How much? This will be a little bit greater than 4.2.
4.329.
4.32.
329.
So can I write 33? So minimum work done. This is the minimum work. Na? This is for the ideal case actually. This is the minimum work. Q1 minus Q2. So it will be 0.13 kilojoule. Na? So the nearest option is this B option. Okay. But otherwise we are getting 0.13. So none of the option is nearby. Clear? Now there is one more way of solving this question. Let me tell you. alternate method. If you don't want to solve by this method, then another method is there. Now clearly, heat removed from inside of refrigerator, that part will remain same. This was 4.2 kilojoule. No? This is also same. T outside was 300 and T inside was 80. Up to this point it is same. Now, what is the coefficient of performance of the refrigerator? It is Q2 by W. Na? Or can I write it as Q2 by Q1 minus Q2 or T2 by T1 minus T2? Can I? So W will be, earlier also we did one question similar to this one. Please solve this one. This will come out to be 0.139, near to that given answer. Please check everyone. Are you getting this 0.139? Yes, anyone?
Sir, I'm getting 0.129.
Really?
Yes, sir. Also.
0.129.
Yes, sir.
Everyone?
Yes, sir.
Okay. Means we are getting the same answer, 0.13 as earlier. Earlier also we were getting this. Na? We rounded that off to 0.13. And there is another way of solving this question also, one more. Can anyone tell me? What can be the third method? So you can see we can use a number of methods. We cannot, Siddesh, no, we cannot. We cannot take it according to, okay. We have to take it according to the question. According to the question, it is 18 only. Na? Only in the last it changes to 70. But when the refrigerator was working, it was 18 only. Na? So we have to take it 18. We cannot. So now, what is the another method? You remember yesterday we derived the relation between eta and beta. Do you know?
Yes, sir.
Beta was actually 1 by eta minus 1 because I require beta. So what is eta over here? Eta is 1 minus T2 by T1. Let us solve for eta first. 1 minus 291 by 300. 9 by 300. So beta will be 300 by 9 minus 1. That is 300 minus 9 by 9. 291 by 9. Is it? So beta is Q2 by W. Na? So W is Q2 by beta. 4.2 kilojoule. Now check. Are you getting the same answer? So you can see we have done it with totally 3 different methods.
0.129.
0.129. So you can see exactly same answer is coming now. Noting a difference of 0.001. So it all depends on you in the examination, how your mind strikes and which method you are opting for solving a particular question. You can see this is the best example. In fact, you might not have seen a question being done by so many methods earlier. Okay. The only thing is you should know the concepts. Then you have plenty of things to do. Is it clear to everyone?
Yes, sir.
Yes, sir. Yes, sir.
So that's all for today, students. So we will continue tomorrow. Still, I'm having some graphical questions on calculation of efficiency. But based on this Carnot engine and refrigerator, it is done from my side. I have discussed all the possibilities. Okay. So now you can practice at your own. Okay, students. Bye-bye. Take care.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.